In this lecture, we derive formulas for the lower triangular matrix and the upper triangular matrix for the LU decomposition or LU factorization of a square matrix. Let A be an n by n matrix that has an LU decomposition such that A equals the product of a lower triangular matrix L and an upper triangular matrix U that has ones in its main diagonal. Multiplying out L to the first column of U, the component L sub 1, 1 of the matrix L equals the component A sub 1, 1 of the matrix A. L sub 2, 1 equals A sub 2, 1, and so on, up through L sub n1 equals A sub n1. And so we have the first column of L. Multiplying out this time the first row of L to the matrix U excluding the first column of U, we get the following set of equations. L sub 1, 1 times U sub 1, 2 equals A sub 1, 2, L sub 1, 1 times U sub 1, 3 equals A sub 1, 3, and so on, through L sub 1, 1 times U sub 1, n equals A sub 1, n. So that solving for U sub 1, 2, U sub 1, 3, etc., we have the general formula U sub 1j equals A sub 1j divided by L sub 1, 1 for j equals 2 to n. We can include j equals 1 in this formula. L sub 1, 1 and A sub 1, 1 are already equal so that U sub 1, 1 will be equal to 1. We do not end up with anything contradictory, just something redundant. And so we have the first row of the U matrix. We alternate the process of decomposing the matrix A between using a column of U and using a row of L. This way we are able to find a column of L followed by a row of U. So we generate the next set of equations by multiplying L, excluding its first row, to the second column of U. And these are the equations that we get. In general, we have L sub I1 times U sub 1, 2 plus L sub I2 equals A sub I2, so that we get this formula for L sub I2. I goes from 2 to n. Multiplying the second row of L to U excluding the first two columns of U, we get these equations. In general, we have L sub 2, 1 times U sub 1j plus L sub 2, 2 times U sub 2j equals A sub 2j, from which we get this formula for U sub 2j. Next, we multiply L excluding its first two rows to the third column of U to get this set of equations. Generalizing for the components of L in the third column, L sub I3 should be equal to this quantity, or that L sub I3 equals this quantity. We then multiply the third row of L to U excluding its first three columns to get this set of equations. Solving for the U sub 3j's, U sub 3j equals this quantity, or the quantity A sub 3j minus the sum from k equals 1 to 2 of L sub 3k times U sub kj, all over L sub 3, 3. Generalizing this formula, L sub ij should be equal to A sub ij minus the sum of the product of L sub ik and U sub kj. If j equals 3 in this equation, then the upper limit in the summation is j minus 1. K starts at 1. In addition, the row number I is at least as big as the column number j. If I is less than j, L sub ij will be above the main diagonal, so that L sub ij equals 0. I goes from 1 to n. In this summation and in subsequent summations, when the upper limit of the summation ends up being greater than the lower limit, such as when j equals 1, so that the upper limit is 0, we take the summation to be equal to 0. Generalizing this time, this other equation, u sub ij on the other hand should be equal to the quantity a sub ij minus the sum of the product of L sub ik and u sub kj all over L sub I. If I equals the row number 3 in this equation, then the upper limit in the summation is I minus 1. K starts at 1. The column number j is at least I plus 1. But we can have I equals j because when I equals j, j minus 1 is also I minus 1, and L sub ij is also L sub I. U sub ij is U sub I. And what do we have here? If not L sub I, so that U sub ij or U sub I is 1, which is precisely what the diagonal entries of U are supposed to be. If I is greater than j, then U sub ij will be below the main diagonal, so that U sub ij will be equal to 0 since U is upper triangular. We now apply the LU decomposition of A to solve the matrix system A times x equals B, where x is a vector of n unknowns and B is an n-dimensional constant vector. We replace A by L times U, so that L times U times x equals B. Let the vector y be equal to U times x, so that y is also a vector of n unknowns. Therefore, L times y equals B. We apply forward substitution to solve for the vector y. The first equation says that L sub 1 times y sub 1 equals B sub 1, so that y sub 1 equals B sub 1 divided by L sub 1. Moving on to the second equation, we find that L sub 1 times y sub 1 plus L sub 2 times y sub 2 equals B sub 2. We solve for y sub 2, and y sub 2 equals the quantity B sub 2 minus the product of L sub 1 and y sub 1 all over L sub 2. Continuing in this fashion all the way to the last equation, we should get this formulation for y sub n. In general, y sub I is recursively defined to be B sub I minus the sum from k equals 1 to I minus 1 of the product of L sub ik and y sub k all over L sub I. I goes from 1 to n. With the components of the vector y now on hand, we then apply backward substitution to solve the matrix equation U times x equals y for x. We begin with the last row. X sub n should be equal to y sub n. In the second to the last equation, we find that 1 times x sub n minus 1 plus u sub n minus 1n times x sub n equals y sub n minus 1. So that x sub n minus 1 equals y sub n minus 1 minus u sub n minus 1n times x sub n. The viewer can check as an exercise that from the first row, x sub 1 should be equal to y sub 1 minus u sub 1 2 times x sub 2 all the way up to minus u sub 1n times x sub n. In general, x sub I should be equal to y sub I minus the sum of the product of u sub ik and x sub k. The index k in the summation starts at 1 more than the index I. So k starts at I plus 1 and finishes at k equals n. Because this is coming from backward substitution, we have a sort of reverse recursion with I starting from n, going all the way down to 1.